So now I want to go back and explain another application of the quantum Fourier transform. So this is called phase estimation. And suppose you have a unitary. U and an eigenvector psi and can compute u to the k easily. Well, what you can do is, and we know u psi is equal to e to the I theta for some theta, because eigenvalues of unitaries are all unit complex numbers. Estimate theta. In 1994, when I figured out the factoring algorithm, the news of this algorithm spread basically like wildfire. I mean, I gave a talk in Henry Landau's informal seminar on a Tuesday about how to do discrete log. And that Saturday, when I was home with a bad cold, Umesh Vazirani called me up and said, "I hear you can do factor on a quantum computer. Tell me how." And there's two interesting things about that. First, and after that, I think I gave a talk at the ANTS number 30 symposium, and Umesh gave a talk about my algorithm at this conference in Santa Fe, and all sorts of people were writing me, asking me for the paper, which of course I had not written yet. And The Economist and other magazines were calling and asking about this, and it was pretty exciting. Anyway, what was I saying? Anyway, Alexei Kitaev in Russia heard about the factoring algorithm, but he couldn't find a paper, so he figured it out by himself, and he figured out the phase estimation algorithm, which can also be used to do factoring. And if we have time, I'll explain how. But so you have a unitary, an eigenvector, and you can compute psi to the k easily. So how do you estimate the phase? Well, let's call this h to the n. And so this is a superposition of all binary numbers. And now what we want to do is we want to, so that's summation x and maybe c. Now let's call it summation k equals 0 to 2 to the n minus 1, c. And then the next thing we want to do is get into k equals 0 to 2 to the n minus 1, u to the k, c, k. So how can we do that? Well, there's an easy way, which is we can apply a controlled u to, do we want the ones bit on the bottom or the top? So this is the ones bit, this is the 2 to the n minus 1 bit. And now let's apply u squared here, a controlled u fourth here, and a controlled u to the 2 to the n minus 1 here. And now what we're going to do is apply an inverse quantum Fourier transform. No, actually, we're going to apply a quantum Fourier transform and then measure. Okay. So the ith bit applies u to the 2 to the I, which means if this is in some, if this represents some integer j, then you apply u to the j. And I should have said we start out with all of these. Oh no. We start out with all of these zeros, and the h to the n puts it in the superposition of all bits, which gives you this. And then this thing gives you k u to the k psi. And the last thing gives you k equals 0 to the n minus 1 quantum Fourier transform. So that's e to the 2 pi I. So this, of course, is just summation k equals 0 to 2 to the n minus 1 e to the k theta times psi. Because each u rotates it by theta, so u to the k rotates it e to the k theta. E2 to the, and then the Fourier transform, you get e to the 2 minus 2 pi over I, 2 to the n, e to the k theta. K psi. Yeah, we need to get these indices right. So j equals 0, e to the minus 2 pi I jk over 2 to the n e to the k theta k psi. Wait, that was k. So make this j. Okay, have I got it right now? Is equal to some, no, I haven't got it right because we need a 1 over 2 to the n here. 2 to the n over 2, 1 over 2 to the n over 2, 1 over 2 to the n over 2, and a 1 over 2 to the n. So this is 1 over 2 to the n, e to the minus 2 pi I, k, j minus j over 2 to the n minus theta, j c. So you should recognize this. This is a, okay, I didn't get that right. 2 pi I k, 2 pi j over 2 to the n minus theta, j c. And this is exactly the same geometric series we saw before, which means that we can just read oaf beta is approximately 2 pi j over 2 to the n. Because if we get anything that is far away from this, the sum is very close to 0. And so it's going to be within, we'll get j, we'll get the exact j plus or minus, order of 1. Yeah?
There's also a sum over k, right?
Yes, there's a sum over k. And it's the sum over k which gives you the geometric series. And the sum over j just gives you this. So we see j with the sum over k, which is the geometric series. And the analysis of the geometric series is exactly the same as it did last time. So that gives you 2 pi, beta is 2 pi j over 2 to the n.